In this lesson, we'll talk about the law of sines and its applications. Also, we'll develop an alternative formula for finding area of a triangle. Since we'll be working with oblique triangles, let's define one first. A triangle is called oblique if it's not a right-angled triangle. Keep in mind that the definitions of trig functions, like SOHCAHTOA or the Pythagorean theorem, cannot be used when solving oblique triangles. SOHCAHTOA or Pythagorean theorem is applicable only to right-angled triangles. So how to deal with oblique triangles? We can't use Pythagorean theorem, we can't use definitions of trig functions, but luckily we have sine law. What is it? Well, assume that we work with this triangle ABC. The sine law says that the sides of the triangle are to one another in the same ratio as the sines of their opposite angles. What does it really mean? Consider the pairs of opposite angles and sides. For instance, the angle A and the opposite side A, the angle B and the opposite side B, or the angle C and its opposite side C. Now we can create ratios between the length of the side and the sine of the opposite angle. For example, A over sine of angle A. This ratio is the same if we use the B pair or the C pair. So looking at the blue pair, the side B, compared to sine of the angle B, is the same as the green pair, the side C, compared to the sine of the angle C. Those ratios can be written as we see here, starting with the side and comparing it to the sine of the angle, or upside down, starting with the sine of the angle and compare it to the length of the opposite side. The other way of writing these proportions would be to compare the ratios of sides to the ratios of sines, like this. Notice that all of the three ways of writing these proportions are equivalent, so we can set them up the way that is more convenient for calculations. Usually, we will have three given data, for example, two sides and one angle, or two angles and one side, and we'll look for the fourth variable, either a side or an angle. A piece of advice: when we set up a proportion, it's good to keep the unknown variable in the numerator. That will make it easier to solve. When do we use the sine law? Anytime that we have a pair of opposite data given. So we must have at least one pair of opposite data given in order to use the sine law. Let's see how it works. Suppose we want to solve the triangle with given angle A of 20 degrees, side A 11 units and side B 7 units. We can sketch the approximate triangle. Here's the 20-degree angle A. That's this one. Side A, which is opposite, is 11 units, and side B is 7 units. What we don't know is side C, angle C, and angle B. So, looking at these three pieces of information, we can observe one pair of opposite data. To set a proportion, we need to consider another pair. We should use the pair that involves side B, as it is given, and the opposite angle B to solve for it. So let's set up this proportion. Sine of 20 degrees, that's this one, over 11 is the same as sine of B over 7. As we see in this proportion, only angle B is unknown, so we have one unknown, we're able to solve for it. We want to leave the unknown, sine of angle B, and then work with other three data. So we multiply across and we divide by the remaining number. Sine of angle B is 7 times sine of 20 degrees divided by 11. Notice that I used 7 in front of sine of 20. Writing sine 20 and then times 7 may cause some errors when evaluating, because the 20 times 7 can be mistakenly treated as the input for sine. So the best idea is to write this factor in front of sine. Okay, so now we can use a calculator To evaluate this expression, we go 7 sine of 20 degrees, bracket, and then divided by 11. Enter. Let's record the answer up to 4 decimal places. That will be 0.2176. So we have the value of sine of angle B, but we need angle B by itself. Therefore, we need to undo the sine function. This can be done by using shift sign to recall the inverse sine function of that number of 0.2176. Let's see this on our calculator. Second sine, and now instead of entering the rounded to 4 decimal places value, we can use the value that is already stored in the calculator by using second answer. That gives us a bit more precision. So enter, and we end up with approximately 12.6 degrees. Okay, this is approximately 12.6 degrees. So we found angle B. We also have angle A, therefore it's easy to find angle C. Since the sum of angles in any triangle is 180, angle C can be calculated as follows: 180 minus angle A and minus angle B. So we have 180 minus 20 and minus 12.6 degrees. That becomes 147.4 degrees. Okay, so we have all angles already. Let's record it here. Our angle C is 147.4 degrees. And now we can use this angle to find the opposite side, C. Let's set up the proportion. C over sine of the opposite angle, which is 147.4, is equal, for example, 11 over sine of 20 degrees, the given data. We should always try to use the given data rather than the values that we already found, unless there is no other option. This will help to minimize the rounding errors. Okay, let's solve this proportion. C equals, we multiply those two values across, and we divide by the third value that wasn't used before. So our C is 11 sine of 147.4 divided by sine of 20 degrees, right? That becomes, and let's use our calculator, 11 sine of 147.4, remember to close the bracket here, over sine of 20 degrees. Close the bracket. Enter. That gives us approximately 17.3. Okay, 17.3. So we already have all the values. 2 angles and 1 side. The triangle is solved. Let's solve another triangle. Here's our triangle. Angle B is 65 degrees. That's this one. 65 degrees here. Angle C is 15 degrees. This one, 15 degrees. And side B is 12. Do we have a pair of opposite data? Yes, we do. The purple one, right? So we're going to set up proportion using this purple pair of opposite data and comparing it to the green pair so we can find C. Okay, let's set up our proportion. C over sine of 15 degrees equals, and the given data is 12 over sine of 65 degrees. Now to solve for C, we multiply across and divide by the third value. Therefore, we have 12 times sine 15 degrees over sine 65 degrees. Again, using our calculator, you may want to do it on your own. We should end up with approximately 3.4. Okay, so one side is already found. Notice that to find side A, we can't really apply Pythagorean theorem because we don't have right angle triangle, isn't it? So how else can we do it? Well, we need the opposite angle. Can we find this angle first? Yes, we can. because the sum of angles in a triangle is 180. Therefore, angle A equals 180 minus the given angle 15 and the other given angle 65. Altogether, we have 100. This angle is of 100 degrees. And now we can use the proportion that will involve this pair A over sine of 100. Okay, A over sine of 100 degrees equals, let's compare it to the given pair of data, which is 12 over sine of 65 degrees, right? So now to solve it for A, again, we multiply across and divide by the remaining value. That becomes 12 sine of 100 over sine of 65 degrees, which approximately equals to 13.0 really, so 13 units. And our triangle is solved. We have two sides and one angle. The following example is an application problem. Two houses are located on opposite sides of a river at points A and B, as on this diagram. Here are the two houses, this one and that one. In order to measure the distance between the houses, so this distance AB, a measurement was taken from a third point C, from this point here, located 350 meters from A. So distance AC is 350 meters. On the same side of the river. Yes, it is. Find the distance between the two houses. Let's call this distance C because it's opposite to the vertex C. If we know that angle BAC, that means this angle, is 62 degrees and 50 minutes, and angle ACB, that means this angle, is 38 degrees and 20 minutes. Okay, this is not a right angle triangle, so the only thing we can use here is the sine law. In order to do this, we need a pair of given data. Well, we have one side given, this is the B side, right? But we don't have the opposite angle. However, we can find it because the other two angles are given. Okay, let's find angle B first then. That will be 180 degrees minus 62 degrees 50 minutes and minus 38 degrees and 20 minutes. Okay, so how to subtract this efficiently? Well, let's subtract first just degrees, leave the minutes for later. So I would go 180 minus 62 and minus 38. That would be 80 degrees. And then I still need to subtract 50 minutes and 20 minutes, altogether 70 minutes. But 70 minutes is 1 degree and 10 minutes, isn't it? Because 1 degree converts into 60 minutes, right? So 100 degrees minus 1 degree is 79 degrees. And then we still need to subtract 10 minutes. How can we subtract minutes from degrees? Well, we need to break 1 degree, therefore change this 79 degrees into 78 degrees, and the last degree convert into 60 minutes, and then it's easy to subtract 10 minutes. That will be 78 degrees and 50 minutes. Obviously, we can use a calculator, enter carefully all these degrees and minutes, and get the answer. However, that's the way that I could suggest to deal with this subtraction if a calculator is not available, or if we don't feel like entering all those degrees and minute signs. Okay, so we have angle B, and now we can apply sine law using this pair of data, and the other pair needs to involve C, therefore that will be this pair of data, right? Let's start with C because that's our unknown. We can keep it in the numerator. So C over sine of the opposite angle, 38 degrees 20 minutes, is the same as 350 over sine of angle B, which is 78 degrees 50 minutes. Okay, now c by itself is multiply the values that we see across. So it's 350 times sine of 38 degrees 20 minutes, everything over sine of 78 degrees 50 minutes. Okay, one more time, let's see how can we evaluate this expression on the calculator. 350 times sine of 38 degrees. Degrees are under the angle list. Number 1. 20 minutes. Again, angle list number 2. Okay, then bracket divided by sine of 78 degrees, angle list number 1, and 50 minutes, angle list number 2. Here we go, bracket, enter. Okay, our side C is approximately 221.3 meters. So we know the distance between the two houses. We can state the formal answer. The distance between the two houses is 221.3 meters. The last thing that we want to look at is another formula for area of a triangle. No matter how the triangle looks like, here we have two examples of triangles. An acute triangle with all acute angles and an obtuse triangle with one obtuse angle. No matter how the triangle looks like, as long as we know two sides of this triangle, for example A and B, and the enclosed angle between those sides, in this case angle C, we can calculate the area of the triangle without knowing the height. The formula for this area turns out to be 1/2 of the product of the two sides, A times B, times the sine of the enclosed angle between the two sides, in this case angle C. How do we know that this formula really gives us the area of a triangle? Well, let's look at the proof of it. Suppose h is the height of our triangle dropped from the vertex B and meeting the side B at the point D. Either in this triangle or in that triangle, doesn't really matter. Then we create a right angle triangle BDC, and the ratio of h over A is the same as sine of angle C, isn't it? So h over A equals sine of angle C. From this equation we can solve for h, which is A times sine of C. Therefore, the area of a triangle, which normally is calculated as half of the base B times the height h, can be written without using the height h. It's enough to replace h by the formula A times sine C, right? So this is our h in a formula. And we end up with 1/2 BA or AB times sine of the angle C. So generally, if two sides of a triangle are known, for example A and B, and the angle between them is known, in this case the angle is called C, then the area of the triangle is given by this formula, 1/2 of the product of the two sides times the sine of the angle between them. Notice that it is not important how we call those sides. It doesn't have to be this one and that one. It could be, for example, this one and that one, because the same justification works for any pair of given sides and the enclosed angle. For example, side C and side B, as long as we have the enclosed angle between these sides. Also notice that this justification works for the obtuse triangle as well. Please convince yourself using this diagram that our proof holds here as well. So this is a great formula to remember, just in case if we want to find the area of a triangle without knowing anything about its height. For example, find the exact area of the given triangle, and what we have here is the 60-degree angle, and the two sides enclosing this angle are of length 3 and 8 units. So the area of such triangle is 1/2 of the product of the two given sides, 3 times 8, times the sine of angle 60 degrees. Normally, if this angle would be any angle, not a special one, we would use a calculator value. However, here we know that sine of 60 degrees is root 3 over 2. If we don't quite remember this, we can always sketch the golden triangle with 60 degrees here, 90 there and 30 there. That's 1, that's 2, that's root 3. It's a good recollection of the special triangle, right? So sine of 60 degrees is root 3 over 2. Therefore, we have root 3 over 2 instead of sine of 60. And here we can reduce 2 with 8, leaving 4 in the numerator, which will be multiplied by 3 to give the answer 12. So 12 times root 3 over 2. We can reduce the 12 with 2 again. And finally, we end up with the exact value 6 root 3. Wow, that's great. We have exact area of a triangle without knowing its height at all. The approximate value of it is 10.4, rounded to one place value. But we prefer the exact value if possible. So let's enjoy this trigonometric version of the formula for area of a triangle.